Hello and welcome to Cashmatics. In part one of this video, what we did was we looked to see how we got from some basic identities to the ones I've got here on the left. Now, these identities aren't going to be given to you in a formula book, so it's really important that you know how to derive these identities. So please watch the first part of this video if you haven't already, and just make sure you can get these identities, and better still, if you can remember them, that would be absolutely brilliant. Anyway, grab yourselves some pen and some paper. We'll go through some examples, and hopefully by the end of this lesson you'll see how we can use these identities to our advantage. So the first example we've got here is sine squared x. Now, people often forget how to integrate sine squared and cos squared. And to integrate both of those, we use a double angle formulae for cos. Okay, whether it's sine squared or cos squared, it doesn't matter. We always use a double angle formulae for cos. And people often forget that, and they use the one for sine instead. So the one we're going to be using here is this one. And what I'm going to do is I'm just going to write it on the side here. So we've got cos 2a is equal to 1 minus 2 sine squared a. I'm just going to rearrange it to give me sine squared a is equal to 1 minus cos 2a over 2. Okay, and just remember that can be written as a half 1 minus cos 2a. So let's just put this into our integral instead. So instead of writing sine squared x, I'm going to write a half brackets 1 minus cos 2x. But because a half is a factor, I can take that outside of the integral sign just to make things a little tidier. So I'll take the half out and then write 1 minus cos 2x dx. And to integrate that, the half stays as it is, and whatever's in the brackets gets integrated, and that becomes x take away. Now cos becomes sine, so this would be sine 2x, but I need to remember to divide by the coefficient of x. And then, oops, we don't need the dx. Let's get rid of that. Plus c is what I need. And we can expand the brackets and tidy it up. So I can write that as x over 2 take away sine 2x over 4 plus c. Now, you don't need to expand the brackets, but you can if you want. The next example is very similar. We're going to integrate cos squared x instead. So this time we're going to be using the identity for cos 2a, which is this one here, okay, because that's got the cos squared a in it. So if I was to rearrange this identity, let's just write it out in full. Cos 2a is 2 cos squared a minus 1. So cos squared a would be cos 2a plus 1 all over 2. So let's just plug this into here. And again, I can take the half out like I did before. So it'd be a half cos 2x plus 1 dx, and to integrate that it'd be a half, and cos 2x becomes sine 2x over 2, and the 1 just becomes an x. Add c, and that would be sine 2x over 4 plus x over 2, add c. So you can see it's a very similar process, but for both of those, for sine squared and for cos squared, we used the double angle formula for cos 2a. Right, so here we've got a slightly different integral. So we need to think which of these identities on the left looks most similar to this here. And hopefully you'll see that it looks like that one. But we do have a slight difference. Here we've got sine 2a equals 2 sine a cos a, but here we've got sine 2x cos 2x, which means the identity we actually need isn't sine 2a equals 2 sine a cos a. It's actually sine 4a equals 2 sine 2a cos 2a. Okay, so it's the same identity, it's just written with a different angle instead. The angle on the left has to be double the angle on the right. So what we can do is we can focus on this part here because it looks very similar to this. And if we were to rearrange this, we'd get sine 4a over 2. So this actually becomes the integral of sine 4x over 2 dx. And that's quite a straightforward integral because sine becomes minus cos, so it'd be minus cos 4x over, now I need to divide by the 4, but there's already a 2 here, so what I get at the bottom is an 8 plus c. So something which looked fairly nasty turned out to be quite straightforward in the end. Okay, the next example. So here we've got tan squared 3x. Now, at first glance, you might think, well, tan squared is quite straightforward, but tan squared isn't in the integration list. Okay, there's nothing we can differentiate easily to get us tan squared. So what we've got to look at is some other way of getting it. And what we can do is we can use this identity here, because tan squared plus 1 is sec squared, which means tan squared is sec squared minus 1. So this would be written as sec squared 3x minus 1 dx. So now what we've got is two terms which we know we can integrate, because the derivative of tan is sec squared, which means the integral of sec squared is tan, and 1's easy to integrate anyway. So this becomes tan 3x over 3, take away x, plus c. Next example. This one here looks a bit more meaty. In fact, I think I might have written it down wrong. And that shouldn't be a squared. There you go. That's what I was meaning to write. So what we've got here is something in brackets. Now, if you don't know where to go with this, just try something. It's better to try something than to do nothing. If you hit a dead end, try something else. So whenever I see brackets, I just expand them. Well, not always, but when I see something like this, I would. So let's have a look here. So this becomes the integral of cot squared x minus 2 cot x cosec x, which I'm going to write as 2 cosec x cot x, because hopefully you should recognize that, plus cosec squared x dx. Now, out of all of these, the things I know I can integrate, this should look familiar. Okay, if you look at your integral list or your differentiations, cosec squared should also look familiar, because that comes from your the derivative of cot x, and just cot squared that isn't familiar. So if I was to rewrite the cot squared using that formula, or that identity rather, I'd get cosec squared x minus 1. Okay, so that's just that bit there. Take away 2 cosec x cot x plus cosec squared x dx, and let's just tidy this up a little bit. I've got 2 cosec squared x's, 2 cosec squared x, take away 2 cosec x cot x minus 1 dx. So what I've got now is three terms which I know I can integrate. So cosec squared comes from cot, but there's a change in sign, so that becomes minus 2 cot x. This here comes from cosec x. Again, there's a change of sign, so that'd be a plus 2 cosec x. This is just minus x plus c. This next example, you might be able to see where you're going with this, you might not, but just try something. Okay, so some people might try to rewrite the sine squared as 1 minus cos squared, or the cos squared as 1 minus sine squared, but that might get you down a dead end. So what I'm going to do instead is I'm just going to rewrite this as sine x cos x squared dx. So just using my indices rules, so ab squared equals a squared b squared. So basically that's what I'm using. That's what I end up with. Now, the next identity I'm going to use from here is this one here, okay, because this is a little bit like this part of this identity. So I can rewrite this as the integral of sine 2x over 2 all squared dx. And I'm just going to tidy this up a little bit by expanding the brackets. And I'm going to get a 4 on the bottom, which I can take out, so a quarter multiplied by the integral of sine squared 2x dx. So that's the first part. Now what I need to do is use this identity to help me change the sine squared into a cos. Remember, whenever you see a sine squared, you've got to use the cos 2a, the double angle formula for cos, to help integrate it. So let's just rewrite this identity. So what I'm going to end up with is sine squared a is equal to 1 minus cos 2a over 2. But because it's double angle, this needs to be double this. Sine squared 2a would equal 1 minus cos 4a over 2. Okay, so let's just put that in our integral. Now because I've got a 2 here, I can take that factor of 2 out, which would make it an 1/8 on the outside. So an 1/8, 1 minus cos 4x dx. And now I've got something which we can integrate. So 1 will just become x. Cos 4x will become sine 4x over 4 plus c. And you can expand that if you like, but I probably wouldn't. The last example I'm going to go through is this one here. It looks a little bit complicated, but just like I said before, just do something with it. And more often than not, you'll get to a point where you recognize where you need to go. So because I've got brackets, I'm going to expand those first. So 1 plus 2 cos x plus cos squared x divided by sine squared x dx. And at this stage here, because I've got a single term on the bottom, I'm going to try and split the fraction. So 1 over sine squared x plus 2 cos x over sine squared x plus cos squared x over sine squared x dx. Now let's try and tidy this up to write it in a way which we actually recognize. So 1 over sine squared is cosec squared x. That's definitely something we can integrate. Plus, now this I'm going to write as 2 cos x over sine x multiplied by 1 over sine x. So all of that is that bit there. Plus cos squared x over sine squared x, which is cot squared x dx. Okay, so we're almost there. Just keep this as it is. Plus, now hopefully you'll recognize this by now. 1 over sine x is cosec x. Cos over sine is cot x. Okay, so you've got cosec x cot x, so that would be 2 cosec x cot x plus cot squared x, which I'm going to rewrite using this like we did before. So we've got cosec squared x minus 1 dx, and we've got something we can tidy up and now integrate. So let's just tidy up first. So we've got 2 cosec squared x plus 2 cosec x cot x cot x. Let's rewrite that again. Cot x minus 1 dx. Okay, so what I'm going to do now is integrate it, and each of these terms, hopefully by now you'll recognize these. Okay, so cosec squared becomes minus cot, so that'd be minus 2. Oops, let's write that in. Minus 2 cot x. Cosec x cot x will become minus cosec, so minus 2 cosec x. The minus 1 will become minus x and plus c. So there you go. So hopefully that's shown you how you can use the identities to help you to integrate. And there's countless examples I could do. Okay, so I'd be here, well, forever doing that. But hopefully it's given you an insight of the kind of things you need to be thinking about when it comes to integrating these functions. So go away and do some practice and see how you get on. And hopefully, like I said, that's helped. And I'll see you next time. So goodbye for now.